Hi, everyone. Let's kick off the keynote session. It's my pleasure to introduce our first keynote speaker of ICSP 2020. Kemelmacher-Shlizerman is an associate professor of computer science at the Allen School, University of Washington. Over there, she directs the UW Reality Lab, where they do research on augmented and virtual reality, computer vision, as well as computer graphics. She received her PhD in computer science and applied mathematics from Weizmann Institute of Science. In parallel to her academic career, she founded the startup Dreambit, which was acquired by Facebook in 2016. She spent 2 years at Facebook building various products. Before that, in 2011, she tech transferred the product Face Movies to Google. Currently, she is also a staff research scientist at Google, where she leads a Moonshot product. She has received many awards, including Google Faculty Award, Madrona Prize, and the GeekWire Innovation of the Year Award. The title of her talk is Getting Things Done, which is about her most recent work in mapping in video communication, 3D sports, and face synthesis. She's going to give the talk now. Make sure to ask questions during the talk through the live chat option. I'll then choose, after the talk, I'll choose from those questions and ask her. Please try to type in your questions earlier so I have time to choose from them. All right, Ira, please go ahead.
Thanks so much, Nima, for the introduction. Excited to be the first speaker of this virtual conference. Interesting times. My title is Getting Things Done, and the reason for this title is that I couldn't come up with anything else, that I just wanted to get it done. I want to talk about 3 different projects today that are honestly not very related, but it's super recent work that I wanted to share with you. And so, yeah, this title is totally not meaningful. A little bit about myself. I'm basically super excited about anything human research, human modeling related. So, you know, how to model faces and hair and clothing and body shape and body pose for all sorts of different use cases and applications. So when I choose my projects, there's very much a big focus. On the other side of myself, I love building use cases and experiences and products. And so I combine both, and a big way for myself to choose projects, research projects that I work on. It's also like, hey, am I going to use it, or is it going to be a really cool and useful thing for others to help others? I'm going to go a little bit about the stuff that I've done previously. I'm not going to talk about all, those things in length, just to mention a few. So we've been doing a lot of work on faces throughout the years, and several years ago we were able to get like very realistic results of to synthesize a video of a person speaking just from audio. If you're interested in that, check out the video on YouTube. I've been also working on all sorts of ideas. This is more on the use case side of things. Cool ideas of trying to show people how they may look like in different scenarios. So this work, for example, was to like, can you, whatever you search for, like a little search engine that you could search for anything, give a photo of yourself, and the system would let you imagine of how you would look like with different hairstyles, hats, even different, you know, even going back in time, like in this example here. We've done work related to hair modeling. So this particular one is to show here she's taking a selfie of herself and reconstructing with a completely automatically her face and the hair with the focus on hair strands in this particular work. I'm really interested in anything like the combination of audio and visuals, particularly for human modeling. And so there are a bunch of projects in this space, sound-related projects in my team right now. I'm not going to talk about those, but the audio-to-body dynamics was a really cool initial experiment in that space, where we learned the correlation between audio to how a person moves their hands when they play a piano or play a violin, and we're able to create an augmented reality application that's given a new music. We have a little avatar that plays this music for us. Again, check it out on YouTube if you're interested. Going towards more full body modeling. In this work, we called it Photo Wake Up, and if you haven't seen it, check it out. The video is pretty awesome. The idea is that, can you take a single photo with maybe a person or maybe human-like thing in this single photo or a painting, and so how far can you push it to be able to push algorithms so that you can reconstruct the model of the human-like shape in this photo / painting and animate it. So that's what we did, and then once you can do that, you could also, for example, apply it on paintings, as we did here on a painting of Picasso, and we built an AR app where the woman here, she's putting headset, Magic Leap or HoloLens, and she can see how the model goes out of the painting in front of her, kind of in big size. So it's pretty cool experience. Additional topic of huge interest in my lab is to work on sports visualization, and we've started that by a paper in CVPR a couple of years ago, where we modeled, given a single video of a soccer game, we reconstructed depth maps of each of the players to be able to see a little bit, kind of see it in 3D and rotate to different views. And I'll show one of the works that I'm going to talk today about is related to sports, and I'll show our progress since then. Yeah, so this is just a high-level summary of kind of sample projects that I've been doing throughout the last several years. I'm going to talk today about, I'm going to start with a new project that's going to appear at CVPR this year. That is called, we called it background matting. The world is your green screen. And it's a very relevant topic these days as well. So good timing on our side. This work is led by Shumdeep, a postdoc in my lab, and a PhD student, Vivek. Their photos are here, co-advised by Brian Curley, Steve Seitz, and myself. All right, so some of you may have seen this video. I'm not sure when it was, but it was on BBC maybe half a year ago. So, and this is a professor giving commentary about an important topic related to North Korea on BBC. And let's watch together what happens.
Scandals happen all the time. The question is, how do democracies respond to those scandals?
And what will it mean for the wider region? I think one of your children has just walked in. I mean, shifting sands in the region. Do you think relations with the North may change?
I would be surprised if they do. Pardon me. My apologies.
What is this going to mean for the region?
My apologies. South Korea's policy.
I just love this video, no matter how many times I watch it. So at a time, that was hilarious and funny, and just a joy to watch, honestly. Now these days, the situation got so extreme that all of us are basically working from home and doing all our interactions with humans over video conferencing, right? And so a big problem these days is that our videos don't look as funny and cute as this one, but maybe more like this. definitely not as exciting. And so the least we can do is to, you know, at least get rid of this background, which is not not as attractive as the, you know, the BBC video. So what can we do? What we would love to do is to just replace this, keep the human in and replace the background completely, right? Also maybe due to privacy concerns, or just you don't feel like showing your laundry out there. So we really want just a green screen behind us that will hide anything and show ourselves in the best possible way. And you're probably thinking to yourself, hey, but Zoom is already doing that, right? So we're now on Zoom and I can replace my background. And you're correct, and it's pretty cool, but it's just not doing it completely well. So, and there are things to improve here. So for example, if you look on our video here, and this is not the extreme version, but you can even here, you see all the issues in the hair area, and you see when there's fast motion in hands, you see that hands starting to disappear. Like, you know, the neck area is all, the segmentation is all wrong and so on. And I'll show it, yeah, so what we, and it becomes even more complicated if, for example, the clothing that you wear matches the background, then your body disappears and things like that. And so we've developed an algorithm. So our work is about making it really this segmentation, creation of a green screen look really, really accurate and nice. So here's an example on the same video of our result. And you can see the hair strands looking really good, and the hand is there, and the neck is segmented well, and so on, even though there are shadows and other artifacts. Yeah, here's a video version of our result. And another example of Ali here standing. The background behind her is beautiful Seattle background from our building. But let's say we want to replace this background. So our algorithm can estimate alpha and foreground. We'll talk about alpha and foreground in a second. But you can see the nice, like, pay attention to her hair, and the how nicely everything is segmented. And we can replace it, for example, with even a moving background, the fountain background, and it looks pretty good. Cool. So when we think about this problem, like, what are we actually solving? So I'll get a little technical on this part of the work, and then less technical on the other ones. So so there are three ways to solve this problem, like if you need to solve it. So one way to go is something that is called background subtraction. This is where we see the different artifacts, zoom-like artifacts, where, for example, when foreground and background colors coincide, that you can see holes in the person and so on. Now, the middle one here is segmentation. And so, for example, we can say there's a human in the photo, and so, or in the video, and now we want to use the best state-of-the-art human segmentation algorithm out there and just remove the background, put the new background in. What happens? This looks pretty good, except that those algorithms are not tuned to work well on the boundaries, on the silhouette of the person, and so we see all these artifacts that are inappropriate to use in those you know, computational photography scenarios. So we want to solve it, and what we actually need to solve is the matting problem. The matting problem means, and this is the result that we get, and so the matting problems means that we would like to estimate this alpha parameter per pixel in a way that once multiplied by foreground and added and then we add to it background multiplied by 1 minus alpha, we'll get the result that you see here. So how do we do that? And alpha means that it's a number between 0 and 1, where, for example, the background is 0 and the foreground is 1, and then everything in between, all those problematic areas on the boundary of the human, they're supposed to get a number between 0 and 1, a continuous number between 0 and 1, to be able to solve the matting problem. So let's see a little bit comparison for videos with the two methods that I just described. Background subtraction, you can see all the artifacts that appear in this case. the result on the top is our result, the result at the bottom is background subtraction. And similarly with the human, like state-of-the-art human segmentation. So the result at the bottom is what happens when we run a human segmentation algorithm and just remove the background, and our solution to matting. So I just grabbed this photo from Twitter that somebody tweeted about the ICCP conference. This is an extreme of what happened with the Zoom session in their case. And so it relates to the artifacts that I explained in the beginning, but this is a really extreme case. So thank you for providing this photo right before my talk. Good timing. Cool. So of course we didn't invent the matting problem. The matting problem is a known problem in the computational photography for many years. And the typical way to think about this problem is that given an image, we would like to create, we usually need something that is called a trimap, where the red pixels here are labeled to mean that this is foreground, the blue pixels are labeled to mean this is background, and then all the green ones are the actually ones that we need to solve for. So these are the pixels that we're most interested in, and then these are the ones that get alpha channel here on the right, alpha which is between 0 and 1. Now, when you think, and usually those trimaps, I mean, there are ways to make those automatic as well, but oftentimes these are created manually. And when you think about videos or making a completely automatic application, having a trimap is not as convenient. Like we can't label create a trimap for every frame of a video, for example. And so instead we came up with the following idea. We said, how about we'll allow a person to take a photo or a video with their phone, like Vivek is doing here. And then what we'll do, we'll just ask the person in the frame to go out of the frame and take a photo of the background. So this is it. So we don't need a trimap. What we do need, we need the video of the person to be, segmented out and creating a matting for it. And we need the background. And it doesn't have to be perfectly aligned. We allow small motion, and this is a handheld camera. And so the algorithm is robust to those things. But this is the input to the algorithm. And then we have two steps, 2 parts for solution. So step number 1 is completely supervised learning. So what we are doing, we use the Adobe Composition 1K dataset, which is a cool data set that has 450 ground truth alpha mats. And then when we compose it to random backgrounds, we can use it for training. So I believe those are manually created or created by artists. And so this way we have, we have the ground truth, we have the input images, and so we can train our algorithm in the following way. So we built a network that gets as input a frame, it gets as input the background, and it gets as input a rough human segmentation, which we made it soft, so we dilated a little bit the edges. This is the input, and then our next step is to build this green box. So it's our context switching block where each of the inputs, the frame, the background, and the segmentation are encoded, and then go into selector boxes together with the image encoder, combined together, and then go through the network further to create the output, which is a rough foreground estimation and alpha map. So this is our step number 1, and it creates okay alpha maps, but it's pretty rough. And one of the reasons is that the training data set is pretty small. If you think about it, we only have 450 ground truth alpha maps, and it's really not enough to train a super accurate network. And so, but it gives us really good prior. And so we start like that. And then our step number 2 is is Gannet Refinement. So we're using a generative adversarial network to do the following. And this works pretty well for us. So again, we give it the frame, background, and segmentation. The green box is exactly what I just described in step number 1. So this creates our rough alpha map and foreground estimation. And then we are training to get a generator that will create really good alpha and foreground in a way that it will be close to the green box, to our rough approximation, so that it won't diverge too much. But the alpha and the foreground that is created by our actual generator, which we call generator real, needs to be able to take the background and apply the matching equation and create a nice photo, which is the real photo. And then we have a discriminator that tells us, is this real or fake? And so this allows us, so this two-step process basically allows us to first train in prior in supervised manner with actual maths, but since there are not many ground truth maths out there, this way we can use as many real photos as we want to train the GAN, which allows us to get pretty awesome results. Here are some comparisons. You can see the top photos here are examples of various backgrounds, people, motions, and so on. The middle row here shows we call it ours Adobe. It means that this is the green box, step number 1, what happens after step number 1, supervised learning. And the bottom row is the final result after the Gannet refinement. Cool. So you can see that some of the artifacts disappeared and our maps are much nicer. A few more comparisons with state of the art. We compared with really quite a lot of works and matching and different types of inputs and so on, and created a video that compares on the same examples. So what you'll see here is typically our result is on the top right, and top right is input image. Ours is on the top left, and the different algorithms that we compare with are in the other boxes. And we are making sure to experiment here with different motions and backgrounds and hairstyles where matching is important. Check out the glasses, for example, in this case. Interesting to see the artifacts that appear in some of the algorithms and how ours handles those. All right. And there are many, many examples of how our students are entertaining themselves at the lab. Cool. Okay, and then a few examples of how, so you saw the green screen creation, and now you can actually replace and put any new background on those images and videos. Awesome. A few more comparisons and limitations as well. So these are the maps that are reconstructed. Also interesting to see what happens when you know, two people appear in the same frame and holding hands, for example, or shaking hands, and how the algorithm behaves in this case. It works pretty well. Here is in the red box here a limitation of the algorithm. If the motion of the person is aligned in some particular way with the motion of the background, things start breaking. So that's an interesting future work opportunity. We've made comparison what happens with the context switching, without context switching. You see that it helps remove the artifacts, especially inside the person's body, clothing, and so on. Some of the future work that people can investigate based on this algorithm. So it would be awesome, right? That if we wouldn't need the background capture at all, maybe we can just train an algorithm somehow to get rid of the background at this point, so that we can do matting with only with just the given video. Our algorithm is not real time, so it is not you know, a Zoom replacement at this point, but making it real time is a really interesting topic as well. A huge shadows and reflections are a problem for our algorithm, so analyzing that would be really good. And handling big camera movement. So it allows we allow handheld camera and small camera movement, but big camera movement is still a problem. Shumdeep and team released the code for this. It's called background matting. Check it out on GitHub. And they also created a pretty cool Google collab where you can just try right away. So check it out. It's awesome. Great. So I will spend the rest of the time talking about two works, a little bit less technical depth, but with pretty exciting results. So the second work that I'm going to talk about relates to aging, and we called it lifespan age transformation synthesis. It is led by a PhD student in my lab, Roy Orel, and Shumdeep and Ohad Fried from Stanford, and co-advised by Alice Shechman from Adobe and myself. So one of the topics that I've been personally interested in throughout the last like 5-6 years since I discovered the problem is how to synthesize a photo of a person, given a single photo, and particularly a photo of a child. How can you synthesize a photo of that child in a different age? This seems to be like a really important, useful, and important problem in case of missing children. Here is, for example, a rendering by artists of this child in an older age, but we don't know if it's correct or not. And we are constantly told that it's a really important way of increasing the chances of finding missing children. So we've been working on that for a while. Of course, there are other applications of aging out there in movies and ads and so on. This is an example from The Irishman, I believe, in a recent movie where De Niro was shown as a, this is the one on the left is an actual photo of him, frame of him, and the one on the right is a younger version of him. And so we've been working on this problem for a while. I have a paper about 5 years ago at this point, focusing only on the face and on children's faces to be able to create aged versions. We had really good results, but it didn't cover the head shape. So it was only focused on inside the face mask. And so being able to do head shape changes, especially in children, is actually a very hard problem. So, and one of the challenges in this particular problem is lack of data. There is really no data that can show the same person over the whole lifespan of their, their lifespan photos of the different ages from 0 to 100 or even to 70, because just a lot of time, and there is no such collections. And we can't put a grad student on collecting this data because the PhD will take forever. Now, dramatic head shape as it changed, as I mentioned, there's a lot of changes when we go from a child to an adult, or even from a baby to an older, like toddler. Head grows. And so how do we model that with algorithms without, good data? State-of-the-art focus on, and this is why state-of-the-art works in this space. A lot of them focus on adult to elderly, because then it's a problem of estimating the texture rather than the shape part of the face of the head. The head doesn't grow as much in older ages. And so very challenging case is child to adult. And another thing that we want to ensure is that we'll have a single network or a single algorithm that can basically give in any age image and a target age, and we'll be able to estimate, as opposed to just looking on pairwise young to adult, old type of just two labels. We want to be able to say 5-year-old to 7-year-old and 5-year-old to 20-year-old and things like that, as opposed to with the same network, as opposed to just two labels that are pretty ambiguous. So the first thing, so how do we attack this problem? So the first thing that we did, we decided to create our own, we labeled a data set which already exists, FFHQ, which is a great data set of 70,000 photographs that is used for amazing results by StyleGAN, a set of papers. And so we took this data set and we labeled it for the following things. So we labeled it with the company for age group information, 10 classes with some confidence score. We labeled it for gender information. And then we estimated, so those two were manual, and then we estimated head pose and glasses and eye occlusion score and semantic map of 19 classes. So this data is available and is out there online. You can use it for not only for aging research, but for other applications as well, if you're interested. Check it out. So I just mentioned that there is not enough, age distribution in data sets. So this one, it's also biased to 20 to 29 or so aged people. But it's a big data set. And so we found that, for example, when we look on 0 to 2 age class, even for that, we see like more than 1,000 photos for females and males, each of the females and males. And so that's pretty good for training algorithms to be found, or at least a good start. And similarly for 70 plus, even we have 700 plus for females and 1,000 plus for males. So not too bad. We built a multi-domain GAN to solve this problem, where we encode age separately from identity. Age is represented by unified light and space to enable continuous shape change. We have 6 anchor age classes to fit largest deformations of head that are represented by age codes. We have a separate encoding of identity because our goal is to create a photo of a person by keeping in a different age, but we need to make sure that the identity is preserved. And something that made our results really look good is the StyleGAN 2 modulated convolutions in decoder. Yeah, so this is a summary. I'm not going to go into the technical details of the network, but it's online. You can check it out if you're interested. So I'm going to skip those parts. Here are example results. So each of the little circles shows it's a GIF, and excuse the artifact. These are some of those are GIF artifacts, but you'll get the idea. So basically, you can see a full lifespan transformation of very different people, like different ethnicities and gender and expression, and the results are really interesting, where you see head shape change and you see the aging process happening throughout the time. All of the photos in each of those GIFs are synthesized and produced from a single input photo. I'll show some examples in the next slides. I'll let you look at them for a second. Some comparisons. So there are commercial products like the Face app that create filters just for fun. So we compared to that for those two inputs. For example, this is a typical Face app. They have old young type of filters. It's not an age-based thing, but that's what they provide. So their old filter provides something like this. You can see that the head shape is not changing. While in contrast, here's our result for the age cluster of target age cluster of 50 to 69. You see that the head shape changed and the some of the other features changed. Another example with the two other inputs and Face app young 2 filter. This is their result, and here's our results of target age of 15 to 19. But we, of course, can do different ages. So here's ours to go to 0 to 2 from the same photographs. We compared with a big amount of previous works in this space, and you can see those in the paper. I'll just highlight a few. For example, we compared with S2 GAN on those 3 photos that are provided in their paper. They're not able to do smaller children ages. This is the results for the older ages. And here the results produced by our algorithm. I'll switch between them a little bit. This is ours. Comparison to PyGAN. Similarly, no results for younger ages. Results for older ages, and our reconstruction, our synthesis for the same photographs. IPC GAN and our results. We also retrained IPC GAN with our own data to make sure that it's an algorithm versus to understand if it's an algorithm versus data. And they provide code, so we were able to retrain. Here's the result of IPC GAN. You can see that it's doing interesting things, but there are still quite a lot of artifacts that happen. So this is our result on the same photographs. Yeah, and I'll finish this part by showing a few more examples. We ran it on quite a few examples out there. So some look pretty amazing, some have artifacts, but you get a sense of how well it works from those. And those are the input photos to those to create those results were in the wide range of baby to teen to adult. So these are produced from different types of ages. I'm particularly impressed in those results by the ability to go from a little baby to adults. It's I think it's special to our algorithm, and I hope more people will work in the space as well. Great. I would like to finish with the third work that is in process right now, and this is related to the space of sports visualization and reconstruction that we are quite excited about in our lab. So this work is led by Lu Yang, whose photo is here on the left, and Kostas, who is a previous postdoc in my lab, and co-advised by Brian Curlew, Steve Seitz, and myself. And the idea is that, so in the soccer work that I mentioned in the beginning, we were able to take a video of a soccer game and reconstruct the depth maps of each player. Depth map means that we cannot hallucinate how the players look like from all different views, but we can just move a little bit. We have some depth perception, and we can move a little bit kind of left, right, and see how things look in 3D, but it's not an actual match of the players. And so in this work, where we switched also to basketball, we are interested in seeing, can we take a single photo, not even a video at this point, due to the so many challenges of this problem, and reconstruct this player with like the highest resolution that we can, including the clothing and including the the muscles and including the crazy body poses and shapes that basketball players are doing. And those are like even the poses are very much non-trivial, because the body pose estimation algorithms that we are training in the community as a general case oftentimes do not include the extreme poses that basketball players are doing. So our goal is to create reconstruction, and for example, if this photo was taken from a camera view that I have this little camera here, maybe it's taken from that side, but we want to see, hey, what if somebody would take a photo from another side or some other side? So we want to see the full span, the 360 reconstruction of this player, to be able to see it in 3D. So how do we do that? That's a really hard problem. The challenges are, so first of all, there is no ground truth 3D data for real games, right? So we have those photos, we have videos. It's really hard to acquire such data. Beyond, so as I mentioned, beyond the soccer demo, we want to reconstruct unseen parts of players, so the full meshes. Something really important is that basketball games have very fast player motion. So, and which has to be accounted by the algorithms that we built, and also a lot of substantial camera motion. And the players are oftentimes in the air, so they're not standing on the ground most of the time. They're actually jumping and dunks and so on. So they're airborne, and so that's an important part that we need to solve as well. In the pose estimation part and also in the shape estimation part, it's actually very significant. So here's what we did. So we decided to, since we don't have 3D ground truth data from games, it just doesn't exist, we decided to use video games. We did it previously in the soccer for soccer reconstruction, but we made it more sophisticated for basketball. And here's what we can do. So there's the NBA 2K19 video game, which we use to capture 3D data with approval from NBA 2K19 creators. So for each frame of the game, of the video game, we used RenderDoc to capture the following details. We could get the triangle mesh, which looks like this. We could get the camera view, and we could get the textures. So those three things we can get from the game. We cannot, the meshes are not rigged, so we cannot animate them or create any new poses. So this is information that we have. From those outputs, we can also create, we can map the texture on top of the triangle meshes and create a textured mesh. And we also have access to skeleton points. So we have access to 3D points on the triangle mesh that represent the different joints. Now, we do not have video information or any other type of information, no animation type. This is the best we could do. In total, the students basically played the game to create the training data, and so we collected body mass and texture data for 27 players, different players, and for each we made sure to collect around 1,000 very different body poses, and again, like basketball-like poses with extreme motions, like example of those you can see here in the slides. Given that data, the algorithm works as follows. So input image, we crop the image, we detect the person and the image, the person that we're interested to reconstruct. We crop the image around that person. Our first step is to retrain state-of-the-art pose estimation algorithm on our data, but also add a few more components in a way that we change the state-of-the-art pose estimation network to also predict jump. Remember I said players are airborne and they're not always on the ground. So jump is very important. Is a person jumping? I'll talk about that in a second. We estimate 3D pose, jump prediction, and 2D pose skeletons. This is what the PoseNet is doing. And then another network is doing the mesh generation that creates a 3D mesh. This is a big contribution of the algorithm, the mesh generation part. We create a 3D mesh. Then we also estimate camera. And we, from the camera estimation, we estimate the global position of the player on the court, on the ground or in air. And we are able to then show results of the reconstruction on the court from different camera views. So this is the overview. Let's talk about PoseNet for a second. Well, it's I'm not gonna get into details, but it's a state-of-the-art pose estimation plus estimation of jump class and jump height, which is very important for basketball, we found. For mesh generation, we have two parts to our network. One is an identity net, which starts from REST pose template mesh of a generic player, not identity related. And then this information plus the information from the input image, which is encoded together, we estimate the vertex offset of the template mesh to create a REST pose personalized mesh. So this is the identity part of the network. And then the second part is, now that we have the personalized REST pose mesh, we divide it to different body parts. So each body part has a separate network. And given this body part of the REST pose personalized mesh plus 3D pose skeleton, this information is encoded and combined together to create a posed mesh. So we basically, this network basically is doing skinning. So it knows, based on new skeleton, it knows how to move the arms. So it starts from rest pose and then it moves to the right pose. We found that this process works very well for us. Some results for PoseNet. It works much better than other algorithms, even if we trained on our own data. We retrained most of them on our own data, on the new basketball data. The mesh generation is working really well as well, and better than state of the art, even if we trained on our data. Some visual examples compared to simple-like methods are not supposed to work really well for those cases because they don't include clothing. But just to show the maybe the pose part, that's what you can evaluate here. So ours are in the orange boxes and ground truth is right here. And these are two views. So we compare to spin and simplify X. So you can see that ours is pretty accurate in reconstruction of clothing and the poses and so on, while spin and simplify is making mistakes. So the previous one was on synthetic data. This is on real data. So the input images are from real basketball games. These are the orange boxes again show our reconstructions, and we have comparison to spin and simplify X in two views. Comparison to, we also compare to methods that reconstruct from single image, including clothing. So text to shape is one such method. And so we compare to that, given two different inputs here. We show results of ours outperforms text to shape for those cases. We compare to PIFO on synthetic data. So this is the original PIFO code. This is the PIFO retrained on our NBA data, our own data. You can see that it's getting better than the original PIFO, but it's still not as good as our reconstruction. And we have ground truth in this case because this is synthetic data, so you can compare. Similar examples on real data where we don't have ground truth, but we can visually compare. Again, PyFu plus NBA is retrained on our own data. Yeah, and this is the final one, is retraining simple on NBA data and showing what can happen per player. Other comparisons with geometry learning methods, there are interesting differences here, especially in the arms area. Like arms get too thin with CMR and 3D coded, for example, the shape is not as preserved and so on. Or like broken, you can see here broken arms, hands, and so on, while ours is pretty working really well. And more comparisons. I'll finish with a video of how it actually looks like. Just before that, some interesting garment details. This is a prediction. Note that the garment wrinkles and so on, the clothing wrinkles change with the different body poses, and so our mass generation network accounts for that and reconstruct the wrinkles. I'll skip some of those cases and some of those details and finish with a video of the different types of reconstructions that we've done. So the input photo is the one on the top bottom, and the reconstruction is what you see at on the as big screen. And notice how difficult are the different body poses, even with motion blur and hard, like fast movements. It's exciting to see on how many diverse examples the algorithm can work and how robust it is to the different types of people and poses and meshes and garments. You can also see some of the issues that, of course, there's a lot to solve yet. For example, in this case, you can see that the food is a little higher than the actual from the ground than the actual in the actual photo. So lots of work still remains, but a very exciting first step in this direction. All right, I will summarize. I talked about 3 works. One was about background matting and how to create Zoom type background replacement, but in a high quality way with matting. The code is online, the collab is online. You can just try it right now if you want. I talked about our progress with aging and synthesis of faces. Talk with Roy if you're interested to hear more. And I showed our newest progress in kind of super fresh progress in the sports visualization to my talk with Lu Yang if you're interested in details. I will finish here. Check out Reality Lab at UW. We have a huge effort if you're interested in like intersection of graphics, vision, AR, VR, and related fields. So we have a huge effort at UW going on with the lab growing pretty fast and really interesting applications going on. Check out the website for what we're up to. For example, now I'm teaching in our crazy times, I'm teaching a VR class in VR about VR, which is pretty interesting experience. So check it out if you're interested. And I'll finish with my own motto, and I will thank you. And feel free to ask questions. Thanks a lot.
Thanks so much. It was a very nice talk, excellent results. There are already several questions. I start with one of my own. In the matching case, do you enforce temporal coherency? Can you comment on the temporal coherency of the results?
It's a really good question. We apply it on videos, but we don't enforce any temporal coherence. It's a frame-by-frame algorithm. Would be interesting to enforce temporal, maybe we'll, yeah.
But the results already were coherent. That was amazing. Here's a question from the audience. This is two questions. I think they are related. They want to know how robust the matting approach is against, for example, change in environment lighting, motion in the background, for example, leaves in the trees and so on, and camera motion. I think you commented on the camera motion as future work, but can you comment on the other stuff?
Yeah, these are really good questions. And for all of those, if there are extreme changes, the algorithm will create artifacts. It is pretty robust for smaller changes for all of those, but definitely a lot of future work here and trying more extreme conditions.
Mm-hmm. Another question from the audience on the aging approach. So there were, in the GIFs that you showed for the aging, mustache and glasses seem to appear as the person was aging. Can you comment on that, why the approach does that?
Yeah, that's a really good question. A big part of the aging process that we don't know how to model yet. So this algorithm focuses on the head change, shape change, but when babies usually don't wear glasses, but adults do, and so obviously biased to the data set. But if we just our network basically learns the difference between identity and the age process, right? So oftentimes it would count adding glasses for adults as the aging process. So it's obviously wrong in this case, and it would be great if somebody will come up with a method that accounts for hair growth, because there could be a person at 60 that doesn't have a beard, or yes has a beard, right? Or has a glasses, or doesn't have a glasses. There's so many different parameters out there, or health-related aging process, or environment, or smoking, non-smoking. All of those things are very much of interest from in the different areas, and it would be great if we can sell those in the future. This work doesn't do that yet.
Mm-hmm. Another question from the audience. In your work on reconstructing the NBA players, what is the loss? Do you put the loss on the comparison against the ground truth mesh and camera pose, or on the rendered images? You use the result to re-render image and compute the loss on the rendered images.
The network takes into account the image.
Mm-hmm.
And there are various losses out there. So the pose part is trying to optimize for the pose that came from the game, and for the mesh generation part, we also the loss is also on the original mesh. It's trained on game data, so it has ground truth.
Mm-hmm. Okay. I'll ask you the last question. This is a question on my own. So for reconstructing NBA players, do you think something like what you did in matting, like adding adversarial loss to train it on real data, would be helpful? To train on real data without corresponding ground truth, basically?
Yeah, that's a really cool idea. We haven't tried it, but it worked really well for us for matting. Specifically, when you don't have enough data, you do this initial stage and then you do refinement. It could be that, yeah, it's something that is interesting to try. We haven't tried it yet.
Okay, cool. Thank you so much. We are out of time. This concludes the keynote session. We have 2 sessions in the afternoon at 3 and then 4:30. Please join them. Thanks.
Thank you so much.